So that's the break. That's all over. So we've looked quite a lot. We've spent most of the day looking at benchmarking, analysing benchmarking data, and then maybe how to some sort of best practice or ideas for how to best collect that data and keep track of it, and what sorts of data you need. Related to benchmarking, so yeah, related to benchmarking, the other side of the coin is what's known as profiling. So benchmarking typically gives us observational data on what performance looks like and what performance variations look like. Now, based on how we've done the benchmarking, we can often postulate why we see the trends we're seeing. So, for example, on the Sharpen example, I think we were able to show from the data we gathered that the serial components, the code which we knew was the I/O and the setup at the start and end of the in the end of the application, were the things that were causing the scaling to fall over, particularly in the overall performance or the overall runtime. So with simple programs, you can often work from the observational data you have in benchmarking to understanding why these things happen. Now, in some cases, it's only the observational data you're interested in. If you're working out how to best use resources, and you're working out, you've just got a new system and you want to know what the best job size is for the problem you're treating, then often the observational data could be enough. But however, if you run into problems and things aren't working as you expect them to, say you go onto a new system and you don't see, it's not the program's actually not working quite right, or not giving the right sort of performance compared to your experience from other HPC systems, then often what ends up having to happen is that people need to profile their application to get a better understanding of what's going on in the application, what's different as it scales up, or as it runs on different numbers of cores or with different parameters and things like that. Now, this is often used by application developers, and obviously this course isn't really aimed at people developing software and things like that, but it can also be useful to access basic profiling when you're just running code. If you find that something's not working, it might point to a problem in the way that in the thing you're trying to do. That maybe some parts of the program doesn't scale as well, doesn't perform as well as you're expecting, and it can give you hints towards that. And it also can provide useful information when you're contacting either application developers to help you out with any issues you see, or contacting the service desk for the service to help you out. So while it's not, I don't think in any way a core thing that people who are running applications and not necessarily developing applications will need to do very often. It is quite useful to know what sort of information you can get out of a profile, and what that and how that helps you understand what's going on and what the underlying reasons for the observed performance you see from benchmarking ones. And actually, it can be nowadays pretty straightforward to get out profiling information. It used to be quite a specialist task to be able to profile a code and then read the profile and understand what's going on. But on modern HPC systems, actually, the profiling tools are generally much more user-friendly and easy to access. So what we're going to do in this section is take the same code again, the same application, the image sharpening, and look at look at what the profiles look like when we look at this application. And this should give us information. Typically, each profile you might have access to different profiles on different HPC systems, but most of them provide the same sort of information. Typically, for example, how much time is spent in different parts of the application, memory and I/O usage statistics, MPI or the parallel approach usage statistics, and differences across different parallel tasks. And that's often where you see something called load imbalance, where one of your parallel processes might have a lot of work to do compared to another parallel process which has much less work to do, and can be one of the major issues in scaling up codes to use one more cores, even if they've been parallelized. And we talked about how amount of code that has to be actually parallelized, particularly in strong scaling, to achieve good performance. And what you can find is that as you scale up, even though the code is inherently as well written and very parallel, And the problem you're treating might be very inhomogeneous, and this could lead to load imbalance. The classic example of this inhomogeneity and load balance issue comes with people who run cosmological simulations. So these are simulations pertaining of the early or the lifetime of the universe, formation of stars and galaxies, and how they do. And if you think about what the universe looks like, even from my limited knowledge as not an astrophysicist, you'll know that there's regions of very high density stars, galaxies, clusters, separated by regions of incredibly low density interstellar space where there's nothing going on. So if you did a naive parallelization and set up a grid that covered the universe, then you'd have some areas where not very much is happening at all in some parts of the model, because obviously there's dark matter and dark energy that permeate into potentially into different places, but there's some parts of it where there's much less happening than other regions. This can lead to load imbalance and could be a big problem for scaling calculations. Anyway, but we're not going to go into profiling in any sort of real detail here, in any huge detail, because that would be a whole course in itself. And in fact, we do offer performance analysis courses, advanced performance analysis courses, where we can take people's codes and really, with the help of an expert from EPCC and HPE, you can delve into your codes and have a look at what's needed, what the profiles are telling us, and what's needed to improve things. But I did want to give you a sense of what's available through profiles and how you might go about running them and getting that data on a system such as Archer 2. So what we're going to do is we're going to use profiling. We're going to run two profiles, one at a lower core count, and then one at a higher core count, and look at the differences between them, essentially. So we already understand the scaling here and what the problem is, which is limited by the serial or I/O part of the application. And when we saw, as we usually very large core counts, we saw the calculation part of the application also shows serious issues with scaling. We're going to use the CRAPAT Lite performance analysis tool to look at this and the information and see if we can try and understand what's happening a bit here, or see how it matches onto our current understanding of the scaling of the Sharpening program, which we've inferred from the observational data we've got. Here we're using a Cray specific tool because Archer 2 is an HPE Cray system. As I said, there are other tools available on different systems. The interface might look a bit different, but the data they provide should be pretty similar across the different tools you might use. So because the Sharpen application is really a toy case, and you've seen how quickly it runs, we've had to modify the application to use with profiling. In particular, what I've done is created a modified version of the application that reruns the actual calculation part, the bit of sharpening the image, hundreds of times to increase its significance within the application. So what this means is the application runs for a bit longer, and it's rerunning the actual calculation time, the actual calculation part lots and lots of times. Okay, so what that corresponds to is a higher proportion of well parallelized code for the application. So it'll change the profile a bit compared to what we're expected to see for the very short application. But if you run the very short application, you just don't get enough data to be able to use it in any real way. So there's a binary in the Sharpen module accessible in exactly the same way. We've been using sharpen-mpi.x. There's a sharpen-mpi.profile.x version of it. And we'll go back to running interactively here. So we can all do this. So I'm going to set this off, but you can set it off too. What I'm actually going to do though first is create a different. I'm going to create a new directory for this. So make the IR Sharpen bench, well, Sharpen profile this time actually. So I'm going to go into Sharpen profile. I need to copy the fuzzy image across again because we need it to be able to run the program. Oh, and I forgot to tell it where to copy it to. So I'm copying it to here. Okay, so I've got the fuzzy PGM, and I've still got my srun opt set up command. And so this time I'm going to do it with 64 tasks per node because the scaling was pretty good at the scaling of the calculation part was actually pretty good at 64 tasks per node, and then I'm going to put the output into this Sharpen 64 profiles.dat, which output the data. So what this executable has is, as well as being augmented with the ability to run the fact that it runs the calculation part hundreds and hundreds of times to increase its significance, it's also been linked to the CRAPAT tool. So when you compile the application, you can enable CRAPAT Lite, and that enables the system to capture the profile information from it. So there's documentation in the RC2 docs on how to do that. It's pretty simple, really. So I'm going to get that running like that. You'll get a message back from the terminal while it's running, just to say that which is the performance analysis tool, and then it should finish. Okay, so now we can take a look at the output file. So let's use less, and it was Sharpen 64 cores profile.dat. Okay, so the first bit is the standard output from the Sharpen calculation. Okay, so so the one thing I'm confused about is it says, oh yeah, there we go. So it's running on 64 processors, and the first rank is on 0. Okay, I'm happy about that. And it does 100 repetitions of the actual calculation bit. So this is just the normal output we get from the Sharpen application. Now, if we scroll down, there's some information from CRAPAT about where the different MPI processes are. Let's get down past that. And then there's this section with performance statistics about the application. Okay. And it has some various bits of some bits of it aren't interesting, some of it are to us. And the things where I've included this sort of stuff idea here. So in terms of what we want to look at, basically in a first pass when we're looking at profiling, we want to typically look at the proportion of time spent in the parallel section. So how much time is being spent in MPI and in what functions. For this case, we also look at the memory use, and we want to look at the IO use, because we know the IO use has been a problem in the past. So if we look through the CRAPAT Lite performance statistics and scroll down, the first thing, or one of the first bits you get to, is this table, okay, which says profile by function. Okay, and that shows you where the MPI time is being taken up in this calculation. Okay, so you can see that, excuse me, so at 64 cores, only 6.4% of the total time is spent in MPI routines, and 61.1% is spent in user, which means actually that's in most of the 61% user, which are the routines that were compiled into the program, and this etc bit is where it uses system routines. So actually, you can see here it's using an exponent routine. That's here. Okay, so this tells you by far the majority of the calculation is spent doing actual calculation, with only a small amount of time spent in MPI communication routines, which is what you'd expect where in a regime where the application is scaling well. Okay, so a small amount of time in MPI for actually passing information, but most of the time is spent doing computation up here, okay, in the user routines. The other things we can look at are how much memory is used. So if I scroll up slightly from the table, there's some basic information on memory usage here and high memory use. So that tells you that in total, the application's using just over 5,000 megabytes. So that's excuse me, about 5 gig of memory, and each of the PEs, a PE is an MPI process in this case, uses 80 megabytes. Okay, so that's somehow storing the data used for the program. and so it's not very high in terms of memory use. Finally, if we scroll down the bottom, we can skip past lots of other stuff. There's various other bits and pieces you can look at. It tells you which lines of the program it's using, but that's not particularly interesting for us here. Some more memory information, but we keep going down. Actually tells you the power usage, which can sometimes be useful for how much power is actually used in the calculation. But finally, down near the bottom, there's the file input and file output stats by file name. So there's a table of input and a table of output. Okay, and what this confirms here is that the input and output is completely serial, because it says here, it's reading in fuzzy.pgm, and the number of reader ranks is 1. So there's only one of the MPI processes is reading in the file. And out here, the number of writers for sharpen.pgm, which is the output file, the number of writers is 1. It gives you some performance statistics as well. But for us, this is confirming that that the I/O is completely serial here, so which is leading to the bottlenecking as the application increases. Okay, so so you can get quite a lot of data quite quickly from this profiling. So what I'd like you to do now, hopefully based on that example, is to have a go at profiling on 256 cores. So I'll go back up to the example where I ran the calculation. So you should be able to run the 64 cores example, check you get the same sort of output that I got that's described in the course docs. Then try and running at 256 cores as well. That's 2 nodes and 2 full nodes, and see if you can spot where the differences are in the profiles between the two runs. That should hopefully give some sort of idea of why the larger runs, even in the calculation part, aren't scaling as well as the runs at the 64 core count, where we knew that the calculation part was scaling reasonably well. Okay, so what's that? That's 10 to 4. So hopefully it won't take too long. So I'll give it 5 minutes in a moment to check where we're up to after 5 minutes, and if we need a bit more time, that's not a problem. We can give people a bit more time after 5 minutes to see where they get to. So people seem to have had go at this. Some people do anyway. There's a few people haven't responded. I don't know if that's just because they're off doing something else, or they haven't managed to make it work. But does anybody who did manage to do it want to say have any ideas about what happened? Any of the changes? Did anything change in terms of the proportion of time spent in the MPI functions? Or did anything change in memory use or I/O use? I'm going to stop the poll for now. I'm going to run the 256 one to get an example out. Yes, George.
I've got a diff of the 2 outputs if it's useful to share that.
Yeah, you're welcome to. Oops, sorry. See, I made that classic mistake of trying to do 256 cores on one node because I'm not completing properly. That's fine. Do you want me to stop sharing my screen so you can share your?
Is that how it works? Okay. Sure. You can talk through what you find though, as the expert.
No, it's okay. It's useful to have a different way of looking at it. Go on then. Could you share your screen, George?
Yep. I think I'll. I think it's this window, right? Okay, so you can't see my control window, but hopefully you can see the 2 files. So does that make sense? So I'll go back to the start. So this is just a way of viewing the different changes. So you can see 64 processes versus 256 processes. If I step down, okay, these are about the process IDs. So the calculation time is different, obviously.
Yep.
and the overall runtime is different, and it looks like, naively, a little bit less than a factor of 4, which isn't too bad.
Mm-hmm.
I can probably ignore all that detail, but then you can see, okay, it looks like it's run properly, 64 PEs, and then 1 to 8 per node.
Yep.
You tell me if you see anything interesting you want me to stop at. These are just, again, metadata. So here we got the process time.
So here's the
memory.
This is where the high memory is. So there is something useful to note about the memory. I don't know if anybody spotted this. Spotted this here, but if you look at the high memory for the large case versus the small case, the memory usage is a lot more, right? And actually, if you look at the amount of megabytes per MPI process, that stayed relatively constant. Actually, it's gone up a little bit, but you always expect a little bit of an increase because when you increase MPI, when you increase the number of MPI processes, because it has to use a bit more memory to keep track of the additional MPI processes on each process. But the underlying number is very much the same. And one thing this is telling you is that this application is replicating some reasonably large data set to every MPI process. Okay, so it's not distributing the memory very well. So as you scale up, the amount of memory goes up by around 80 megabytes per MPI process. So while the memory usage still isn't very high, it's only 20 gig or something here across 2 nodes. If you took a program like this and kept trying to scale it and kept trying to push it up to higher and higher numbers of MPI processes, eventually you'd run into problems of running out of memory, right? And this is, if you think about this, is exactly the opposite of what distributed memory is supposed to do. In some sense, the idea of distributed memory parallelism is that you can treat bigger and bigger problems by distributing the memory across multiple systems. So the way this application has been programmed is not very scalable. Now, I know exactly what happens here. I happen to know, exactly what happens in this application is very simple. And what it does is it takes a copy of the whole image and sends it to each MPI process, and then just tells each MPI process to work on a subset of the data. Okay, that's the easy way of programming it for a small toy problem. But in reality, what you probably want to do is read in it on at the start, and then just actually distribute just the bit the MPI process was working on into that processor rather than the whole image. Okay, so there was something interesting in the memory. Yep. So the totals are slightly different. Yeah, so the total number of samples is different, and that's because it ran for a shorter amount of time on the larger number of cores. So the total number of the samples, because it takes it on a regular interval, is smaller. That's all that one's telling us. So where did we get? You had one further up that was user.
Space. Sorry, if you go. Yeah, okay.
It's okay. So that's gone down a little bit by about 5%, just over 5%. Amount of time in use has gone down a bit, so we can keep going down and look at ETC and then MPI. So the ETC one's gone down a bit as well by again about 5% or so, maybe a little bit more this time, 6 or maybe 8%. And then the MPI totals have gone up from around 7% to just over 20%. There's some slightly different routines involved. So before it was barrier and bcast, now MPI reduce is appearing as well. But actually, it's the MPI bcast time and the barrier time that's gone up a lot. So what this is telling you is essentially there's much more overhead in doing the MPI calculations now. And so if you went and ran again on, as it says, what happens if you double the core count again to 512 cores? And what you'd see, I think, is that MPI time would continue to increase. So what that's telling you is it's the parallel message passing, that the actual business of doing the parallelization, the overheads associated with that are increasing as you increase the number of cores, and that means that that's what moves you away from perfect scaling, right? It's because the overheads become larger and larger and larger for the actual MPI. And again, it's a bit like what we said before about the airplane and the serial components and all that sort of stuff. You know, the calculation bit can get faster and faster and faster, but if the overheads for the actually splitting up the calculation grow and grow and grow, then you lose the ability to scale. Okay, and this is where you end up with the problems with parallel programming and using and scaling of parallel calculations, particularly in strong scaling to larger and larger sizes. Okay.
Like go down to one of the lower tables.
No, I think that's mostly what we're interested in. The only other
Okay.
thing would be the IO one, and that should be that should be almost exactly the same.
That's
Okay.
the last table, isn't it? Here we go.
Yeah, so I can share my screen again.
Okay,
That's
I'll cancel.
And then stop. Thank you. That was a useful diff to be able to see the two things in one place. Oops, that's the wrong thing. Share screen. Let me go back here. Okay, so you can see my calculations again, and you know, that was the 256 cores. I could do the 512. It would take very long, I wouldn't have thought. So the number of cores per node stays the same at 128, but this time I'm going to use 4 nodes, double the number of nodes. It takes a bit of time to run. There is a little bit of overhead in running the profiler as well, which slows it down a bit, but so here's the usual output, and we should get down to the ClearPath Lite bit. Performance statistics. You can see the memory usage has doubled again. Okay, which as I said is not good. Now you can see the MPI is now up at 30.4%, and it keeps increasing as the overheads increase and increase as you increase the core counts. So there are problems with this code that you could see from there was sorry, one problem from we saw in the profiling that wasn't evident from the measurements we'd done on the code was this problem with the memory, this potential problem with the memory growing. You know, so it did reveal something we couldn't have, we didn't obtain from our observations that may cause potential problems in the future. I know this is only toy code, so this isn't really. And you know, we verified that actually the problem with the calculation not scaling or moving away from ideal scaling as you increase the core count is because of the increase in the overheads of actually doing the parallelization itself, which is not free in this case, because processes do have to exchange data to be able to make the sharpening algorithm work. And also there's obviously the sharing out of data, the gathering back of data at the start, and the gathering back of data at the end as well. Okay. So the profiling can give you a different sorts of insights, or it can at least point to where the problems might be. I mean, this is typically what you see if the program's been parallelized reasonably well in terms of MPI, at least ignoring the memory problems, but you're just scaling beyond the useful limits of scaling for the code or for the problem you're treated. If we had a bigger image that we wanted to sharpen, then I suspect you'd find that you could scale, you could scale out to higher and higher core counts without introducing without these overheads being the same problem. Okay, so what profiling should do is actually give you some insights into why the scaling of your application HPC system is varying in the way it does, and you know, it also potentially allows you to predict performance on different parameter values without running the benchmark. You know, so in this case, you know, I've seen how, you know, I've got 3 data points here, so I can plot how the MPI time is increasing, and I'd be able to extrapolate that, you know, and say, you know, actually, I could then postulate about what the performance is going to look like in the future. Now, I could do the same for the performance graphs, but the other one here I could do is plot the memory usage at those points and extrapolate out to how many cores I'm using, what the memory usage would look like, and predict what it could look like on higher core counts for this problem and this problem size. So it gives you more data that you can potentially use to analyze the performance. Now, in general, as I've said a few times, I think people who are profiling and running, people who are just running applications and want to know mostly about, you know, how to use their resources efficiently, probably are going to end up stopping at the benchmark stage. You know, do some simple benchmarking identify for that particular application, which is the code plus the input, what the right trade-off between time to solution and efficient use of resources is, and then use that to run. You know, it's only really if you're going to run if you run into problems and issues with your calculation in terms of maybe running out of memory or not scaling as well as you'd like, or not seeing the performance you'd expect based on results from other systems, that you might start to do some simple profiling to try and understand what's going wrong. I mean, typically, if you've got to that stage and you're not confident and comfortable with the profiling, you can usually either engage the support team for the HPC system working on, you know, for example, on Archer 2, you know, if you email in, you can get access to the expertise from EPCC, you know, to help you profile, understand, and find problems and solve problems and workarounds if possible for your code. But also, you may have, for example, your local institution or organization, you might have some research software engineering group or support who'll be able to help you out as well, who have that sort of expertise to help you out there. But I just wanted to give you a flavor of what profiling could offer, so you know potentially what the opportunities are there for gaining more information about using facilities efficiently, and maybe things you might be interested in the future. So profiling is really a very large topic in itself. We've only scraped the surface. These very simple profiles are useful for getting a quick overview of what the application is doing. You can get more and more complicated and use more and more layers of profiling to understand more and more and really dig in into the application and understand how to improve it going forward. If you're interested in learning more about this topic, there are plenty of the courses out there that can help you, and we run some of them, but there are various other ones either from other HPC centres via the PRACE Advanced Training Centres, PATSI, and also from US sites and things like that as well. So profiling, this basic profiling anyway, allows us to see what routines are consuming runtime in our application. Can also provide information on the memory use and the I/O, and often actually the memory use is something that people don't generally have a good handle on, and is important for even people who are just running applications rather than developing code themselves. So if you're really struggling to get applications running, you know, because you keep hitting memory limits, out of memory errors and things like that, one useful thing you can often do is profile to actually get a measure of how much memory your application is using. You can also access information on memory use directly through Slurm itself. There's information on the Archer 2 documentation in the profiling section about how you can access memory usage information via Slurm rather than having to actually go through the whole steps of running CRAPAT. So there are different ways to do these things as always. And I think one of the key things I want to show here is actually an individual profile could be useful in itself, but actually looking at profiles at different parameters, node core counts in our case, but then different input parameter values as well, can be more revealing than actually using just a single profile, because it's the difference often that matters rather than the absolute values. It's how things are changing that matters really. Okay, so that's the end of the actual material for the course. I know we were supposed to run to 16:45, but we've gone through it a bit quicker. But that's also useful anyway. I think in some sense. So what we've got. One question people often ask or wonder is, where do you go next with this? Well, hopefully, it's given you some useful ideas and tools that you can put into practice for your own research workflows, and particularly the HPC part. Some things to think about, and maybe that you could do to improve how things are working, and understand how best to use your HPC resources. And like I say, you can keep, you know, your course accounts will be valid for another few weeks at least, and you can you know, investigate further on the system using Archer 2 and benchmarking, writing scripts, whatever you want to do. If you want to carry on with that, if you think of any questions, you can get in touch with us and ask those questions, and we'll happily get back to you, or even set up a session to like a tutorial session where we can chat and meet and do those sort of things if you want that. In terms of where you're going next after this, there's more training available if you want. In particular, I know Archer 2 offers a lot of courses covering different things. You can see the ones that are available on the Archer 2 website at the moment. In particular, following on from this course, there's various package use on Archer 2 courses. So we've run ones been passed on, for example, getting the most out of some particular programs. So CP2K, material science program, LAMPS as well. We've done, I think we've had GrowMax as well. I know that some people, some of the groups that use Archer 2, for example, the NCAS people who use a lot of the Met Office Unified Model Offer course on how to get the most out of the Met Office climate modeling tools on Archer 2, for example. So there's various courses like that, look at specific software packages. If you're really interested in performance analysis, then we do have a performance analysis workshop. I'm not sure there's one right in the schedule right now, but they do run, I think, at least once a year, and sometimes more than that, where we can take a particular code or an application that you're interested in, a case that you're interested in, and with help of some experts, take a deeper dive into it and understand its performance and how to potentially improve its use on Archer 2 or other HPC and or by extension other HPC systems. In terms of Archer 2, if you're carrying on using Archer 2, there is the documentation. It's got a very extensive user and best practice guide, which has got lots of useful information, including information on tuning and improving performance of applications, as well as all the normal sort of functional stuff. There's the service desk, always happy to answer any questions, as I've mentioned a few times, even questions about this course. So please do get in touch and mention you're on the course, and if you've got any questions, and potentially I was the tutor, and we can help you out. We can help you out there. There are various access routes to Archer 2 as well. If you don't currently have access to Archer 2 and you want to get access, in fact, there's a call open at the moment, particularly if you're UK based or have links to UK research institutions that you'll be able to apply through to get compute time on Archer 2 without having to go through a full grant application. It just gives you access to computer time. Other questions around the use of HPC that aren't particularly Archer 2 specific, then we can always do it. We're always try and help people, but also you might be able to get help from a local research software engineer. And there's two links there to the Society of Research Software Engineering, who are the umbrella organization for groups such as this that provide this sort of research support around computing. It's not just HPC based; it's more general computing as well. But to UK RSE groups and international RSE groups. In terms of training, the other thing I'd mention, of course, is the people we've borrowed the template from here and the style of teaching, which is the carpentries. They have a huge amount of courses out there that are freely available, the materials freely available, and they're very often running at various times, or you can follow through the material yourself online. And thanks to them for making all that stuff available. It's very generous of them, and we make a lot of use of it, both in the courses we run and obviously, as you've seen, in the new courses we develop here. And yeah, apart from the obvious, which I'll ask if people have questions or want more information on anything, the other thing that will happen is you'll get a request for feedback. So please do fill it in, both good and bad feedback. That both of them help us improve the course. I've taken some notes from teaching it today and things that could be improved, and that I've spotted along the way. But we'd love to have your feedback too, as well, to help us try and make this as useful as possible to people. So please do fill that in when it gets sent out to you by our training coordinator. But other than that, then it just leaves me to say, I really want to say thank you all for coming along and engaging so positively with the course, and I hope you found at least some of it useful. I'm going to stick around here, obviously, for a wee while because we finished early. So if people have questions or want to ask things that are particularly related to what they want to do with HPC, then I'm happy to stick around and answer questions for a wee while and have discussions on that. Otherwise, if you want to get away, I know everybody's super busy and sitting online all day is quite tiring anyway. So please feel free to escape. Don't feel bad about just escaping if you want to do that. Yes, other than that, thank you very much. Happy to answer any questions. Oh, and thank you so much to George and Zoo, who have helped out on the course as well, because without them it wouldn't be possible. It would be so much more difficult to run.